Chapter 12 is on the goodness of fit tests, so let's get started. We have the book claims more hockey players are born in January through March than in October through December. And here's the data table for that. Let's go ahead and pull that into StatCrunch just to have it there. And we're using the level of significance alpha 0.05. And we're asking, is there enough evidence to suggest that hockey players are not uniformly distributed throughout the year? So it's reasonable to assume for the null hypothesis that they are uniformly distributed. And so our alternative then is, are they not uniformly distributed? So are all of the population proportions the same, or are they different? That's really what we're looking at here. That's what the goodness of fit test does. So distribution of hockey players is uniformly. More hockey players are born in January through March. I think that one's correct. Maybe that's the correct one though, because this is uniformly distributed or not uniformly distributed. They're not all equal. Yeah, I think B is what we want there. Just uniformly or not uniformly. Okay, compute the expected counts for each birth month. The total number of hockey players is 172. So the expected would be that they are all uniformly distributed. In other words, that between the 4 months, right, there's going to be each of them are going to have 172 divided by 4, 43. That's the expected. The test statistic is going to be in here. We're looking at the probability proportion, right? So let's go ahead and look up goodness of fit test. This is a chi-squared test. That's the whole test statistic. Looks like that fancy X. Just show you again. That's the chi symbol, or chi if in Greek or something like that. But that's what this is right here. It's the chi-squared goodness of fit test. So the observed is the frequency. Expected is they're all equal. As you can see, the probability is 0.25. That's what we expect, is they're all equal. So you can either select the column of the probability or just say they're all equal, and then compute. And so here we have the chi-squared test statistic and the p-value. So the chi-squared is 13.5814. 0.581. It just run in 3 places. P-value of the test, well, we already have that, is 0.0035. What's the 3 places? So 0.004. And is it significant? Yeah, the p-value is less than the alpha value. Therefore, there is enough evidence to say it's statistically significant. So yeah, that'd be part A. Okay. All right, let me see what I did wrong here. Of course, I read the problem wrong. It says, do the hockey players follow a uniform distribution? I thought it was saying, was there enough to say, or to reject H, not all that thing? That's what I was thinking of. So the answer here is no, they do not follow a uniform distribution because we rejected the null hypothesis. So I was thinking, yes, reject the null hypothesis, and then there is significance. So it's because the calculated p-value is less than the given level. So point in case to always make sure you read the problem. It may not be exactly what you think. So if you check those answers, that's all correct. And we can move on. Okay, so we have characters trying to determine whether or not the Poisson probabilistic model can be used to describe locations of the rockets. So you don't really have to worry about what the Poisson probabilistic model is. It actually kind of talks about it a little bit down here. I do recommend you look it up on your own if you want to see more about that. But we do have what it is and we will follow that. So don't worry about that if you were to see a question like that, though you probably wouldn't in the homework. They divided the city into 0.25 kilometers square regions, and they counted the number of rockets that landed in each region. And so this is what we have right here. And then we can estimate the mean number of rockets hit in a region by computing mu equal to the sum of x times ex. Open this in StatCrunch. Okay, so we want the mean. It's really the expected value of that, of this data. So let's see. I can quickly calculate that. Okay, I can't think of a way of doing it fast with this, so let's just do the calculation itself. What we're doing here is just calculating the expected value. So we're gonna have x is the random variable. That's the same thing as the number of hits. And then p of x is the probability that it lands. And we have the observed, so we can use those to find a probabilistic expectation of what it is. So what we're going to do is we're going to take all of these things, add them together, and then divide by the total to get the probability of each. So let's first find the sum here. I can do that pretty quick by just calculating it. 229 plus 208 plus 99, 31, 8, and 1. 576 is the sum. And now let me actually do compute expression. We're going to use the observed number of the rockets that hit each region, and then we're going to divide that by 576, the total. And that should give us, yeah, the probabilities for each of these things. Now, what we're going to do is we're going to multiply the two of them together, the x value and the p of x value, to get our expected. So that's going to be our next column. We're going to take number of hits times the division, see if that works. Okay, we get 0 times this is 0, so that makes sense. 1 times this probability is that, and then 2 times that looks to be about that. So that looks to be about right. And now we can add them all up. So let's go to data, compute expression. What I think we can do is sum the column we just made. I think that's how you can do that. And that gives you a single sum. And so the mean looks to be 4 decimal places, 0.934. Okay, so once again, I just added them up and then created a probability out of each one of these by dividing these by the total. That's the proportion that they are. Also, we can assume that's the probability as an estimate. And then you multiply that by the x value, and that gives you your expected value, or the mean in this case. Okay, so I didn't do this in the last one. The requirements for the goodness of fit test. In the last one, we had, I'm not going to go back to it, but in the last one we had all the things were equal, and they were all above 20%. And so it really was designed to be used for the chi-squared test. But for this one, we actually cannot use the goodness of fit test because, let's see, all expected counts are not greater than 1. You can see there's a bunch of them here that are 0. 5 and 6 are both 0. More than 20% of the expected counts are less than 5. No, you want at least 80% to be greater than 5. That's the same thing, I guess. 80% to be greater than 5, more than 20% are expected less than 5. But that's really the main thing. It doesn't matter if it's normally distributed because we're trying to fit the data to a Poisson probabilistic model, and that's not normally distributed. The data are not categorical, that doesn't matter. So I'm just thinking about A. Let's look at the textbook again for the requirements. I'm pretty sure the textbook says 80% are greater than 5, which I believe is the same thing as that. All expected frequencies are greater than or equal to 1, which of course is not true. Oh, it says no more than 20% of the frequencies are less than 5. No more than 20% of the frequencies are less than 5. And here we have 1, 2, 3 frequencies that are less than 5 out of 8 total. 25 or 20% of 8 would be, well, 25% of 8 is 2. It's got to be less than 2. And this has 3. So definitely more than 20% of the expected counts are less than 5. So that also fails to meet. So both of them fail to meet. So what do? Well, what we can do is we can actually consolidate the table and create a new distribution where instead of having 0, 1 through 0 through 7, we have 0 through 4 plus. That's what it says here. 0, 1, 2, 3, 4 or more. And that just creates this whole block of zeros and 1 to just go away. So it's an effective way to meet the requirements, and that we can continue using that. Okay, so we're going to consolidate the table and use the Poisson probabilistic model using this. This is the probability distribution. This is how you know what the probabilities of each unknown, or the x's are. Mean is the mean from part A, so it's going to be 0.934. That's what mu is for both of those. Find the probability that 0 hits the region, and then all the rest of them. So really all we're going to be doing here is plugging in values into this and finding the probabilities according to the Poisson probabilistic model, not according to the data set, just the Poisson. Okay. So this can be a little bit weird. This is actually a lot easier to do on like on a graphing calculator, because you can see the data. I'm just going to be using this thing to try and show you the actual calculation. And what we need to do is we need to use mu equal to 0.934. So we're going to have on top 0.934. Oops. Okay, and that's going to be to the power of x. Now, x is the number of rocket hits, and so in this first one, x is 0. So we're going to be put to the power of 0. And then that's going to be divided by x factorial. X factorial is going to be 0. Let's see. Factorial. Oh, it's right here. The exclamation mark means factorial. And 0 factorial is equal to 1. It's stated equal to 1. Factorial, if you don't know, factorial is just, so for instance, 5 factorial is 5 times 4 times 3 times 2 times 1. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's how it works for all of them. 0 factorial is the unique one, but the pattern works out to where 0 factorial equal to 1 makes a lot of sense. So that's what we have there. That's why it says 1 there. Okay, now that's being multiplied by e to the power of negative mu. So we're going to have, we're going to plug in negative mu first. That's how this calculator works. And then we're going to hit e to the power of x. E being the Euler's number. It's, I believe, 2.27 or 2.72, something like that. And then hit that. Nope, I forgot to negate it. Let me redo that. Okay, now I can do E, and e to the power of that equals this. Now all I have to do is hit equals, and that is the probability for the Poisson model for this this data set. Wants 4 places, so 3929, but that gets to 10, so 3930. Double check that. 0.3930. Yes. Okay. Now it wants the probability for 1, 2, 3, just all of them. I don't really know why it said for just 0 and then the rest. So I'm going to do the same thing for the last 4. I recommend you try it on your own and then check to see if you get the same thing I do. Okay, I've just filled in the last 4 probabilities. Again, I just plugged in mu is always the same between all of them, so that's 0.934. And then x changes. X is going to be 1 here, 2 here, 3 here, and then I used 4 here. I didn't think about that. Really should have done probably 4 and 7. Hang on. No, that can't be right. This has to be the remaining proportion or probability of out of 1, right? Because probability always has to equal 1. So what we want to do here, because this is 4 or more, I just thought about this. I mean, you don't want to plug 4 into here because it's 4 and 5 and 6 and 7. You could do 4 and 7, calculate both of those and just add them together, but you don't need to. This is the last one, and we know all the other probabilities. So all we really need to do is just do 1 minus 0.3930 minus 0.3670, 1714, and 534. Because again, probabilities always equal 1. So with the last one, we can just use process of elimination. So 0.0152. If you add those all up, they should equal 1. Okay, continuing on. Now, 576 rockets were fired. Determining the expected number of regions hit by computing expected number of regions equals n times p. P is the probability of observing a particular number of regions hit. So that's kind of what we did previously before, is we're going to take the proportion or sorry, it's not what we did before, because what we did before was just we're using this. We're using the p probability from the table we just found. So we're expecting this being the probability, and we're going to multiply these by 576 to get the expected number based on the Poisson probability model. So all we really need to do is just take 0.3930, multiply that by 576, and that is the expected number for 0 rockets hitting it. 3930 times 576, 226.337. Of course, 0.37 of a rocket doesn't make much sense. It could make a little bit of sense in this case, since the rocket could hit on the border, but it's a little bit harder to see, to note what proportion of it gets put on there. But even still, you can see that that's very close to the observed. Okay, moving along, let's do the next one. 367 times 576, 211.39. Let me just go ahead and fill in the rest. All right, I got 211.39, that's pretty close. 98.73, very close to 99. 30.76, that's about 31, and then 876, that's about 9. So these are all very close to the observed. So the Poisson probability model looks to be, quite accurate. Okay, so conduct a goodness of fit test. So again, this was just talking about a certain probability model. And now we're going to actually do the goodness of fit test on it to see if it fits the data. So, do the rockets appear to be modeled by the Poisson random variable? And then P0, P1, P2, 3, 3, or 0, 1, 2, 3 hit rockets hit, and let P4 be 4 or more. Okay, so that's what we're looking at here. Is we're asking which what's the null hypothesis in the alternative? It can't be B and C, obviously, because for the Poisson probabilistic model, they're not all equal. They're definitely different. So, plus also P0 is not in either of these, so it can't be this one. It's going to have to be A or D. Now, which one is it? Well, if you think about what we talked about in the previous problem, the idea was that all of the hockey players had the same birthday. In other words, that they are all equal. It's a uniform distribution. So we're saying that the data fits the uniform distribution. And then the alternative hypothesis was that the data does not fit the uniform distribution. Here, we're not talking about a uniform distribution. We're talking about a Poisson distribution. So it's reasonable to say the null hypothesis follows the Poisson distribution, and the alternative does not follow. It's the exact same thing we did in the first one. They're all equal, as in they're all uniform, so it does follow the uniform distribution. And then the alternative was it does not follow the uniform distribution. So that's what we're looking at here. Is the rockets can be modeled by a Poisson random variable, and the rockets do not follow a Poisson distribution. Of course, null hypothesis is where they do not, and then they do. That's reverse of what we want. So we really want A here. Okay, and now we can just test it. Goodness of fit test is what I'm looking for, chi-squared. So the observed are written there. Now I do actually need the expected. Let me get that written in here. Give me 226.37, 211.39, 98.73, 3076. Okay, so we have the observed here and the expected in var3. Okay, let's compute. 0.094. Whoops. Okay, p-value. P-value says 0.9989. 4 places, so yeah, all of them. And of course, that's a huge p-value. It really doesn't matter what alpha you choose. I don't even think they stated alpha anywhere. That's so large that it would always pass it. So we do not reject H0. There is insufficient evidence to reject the claim the rockets can be modeled. Nope. There's sufficient evidence to reject the claim that the model strikes. There's insufficient evidence to reject the claim the model can be striked. So I know this wording can be weird, but there's a reason for it. It's kind of almost like hedging the bet against it. There's insufficient evidence to reject the claim. So think about rejecting the claim that can be modeled by a Poisson random variable. That's not true, right? So that's why it says there's insufficient evidence to reject the claim. Now let's check it. And those are all correct. Okay, in a survey, we have response were asked to disclose political affiliation. Would you be willing to pay higher taxes if tax revenue went directly towards deficit reduction? A contingency table determined whether the results would suggest there is an association between political affiliation and willingness to pay higher taxes. So that's what we're looking for here. Alpha is 0.05, and we have the results of the survey. Now, what you can do is take this, put it in StatCrunch, and what we're going to do is we're going to, I believe we can create table contingency, with the data. So as you can see here, the row variables are Democrat, Independent, and Republican. So that's going to be political affiliation is the row variables. The column variables are, of course, yes or no. So yes or no, willing to pay taxes. Now, we actually can do all this stuff. We know we're going to have to do a chi-squared, and we have a chi-squared test for independence selected right there. And we don't really need any of this information. Confidence level is correct. We wanted a 0.05, so that's good to go there. And we can compute. And so this actually did everything for us pretty much. We're still going to end up plugging in the data here for the table. You can see here it says no and yes, so that's just opposite of what this has. I'm pretty sure it says no first because no was the first one stated. But Democrat, no is 7, yes is 9. Okay, Independent says 13 no, 4 yes. Republican, 13 no, 4 yes, so same. Double check my work. 944, 7, 13, 13. 15 total. I don't know if it said what the total was, but that's what we have here. All right, null hypothesis and alternative. We're not focused on individual like parties. So those can't be the null or the alternative. We're looking at the entirety of it, the entire table. So that's the reason why those can't be allowed. So it's going to be this and this, because all the rest of them are specific. The question is, which one is it? So if we think about it as kind of like a uniform distribution, right? If everything was all random and everything like that, then that means that there would be a uniform amount in each of the different parties. So Democrat, Independent, and Republican. You'd expect a uniform in yes and no, and that yes and no just depends upon, whatever situation is going on at the time. So we expect that it's always uniform, and the parties don't dictate it. It's always uniform between the parties. In other words, the party doesn't change, it doesn't affect the willingness. And that means that they are independent of each other. They don't affect each other. But what we're asking is whether the results suggest there is an association. In other words, that the party do affect the idea. So that the affiliation and everything are not independent or are dependent. One changes the other. That's what dependent and means. Independent means one does not affect the other. So that's, I believe that's the idea there. Okay, let's continue. The test statistic is right there. 5.191. P-value is 0.0746. 75. Alpha is 0.05. So that means we do not reject it. The p-value is higher, so we do not reject. The data from the samples provide insufficient evidence to conclude that they are not independent. Insufficient to conclude the alternative hypothesis. That's what the alternative hypothesis is there. All right, let's check that. And that's all correct. All right, in a randomized placebo-controlled study, so 1,013 healthy women, 45 years of age or older, were randomly divided into two groups. All right, group one received a drug, group two received a placebo. So in other words, they did not receive a drug. A placebo has no effect on a person. Women were monitored for 10 years and experienced a cardiovascular event. So in group one, $12 experienced a heart attack, and 512 in group two, 16 experienced a heart attack. Okay. So what is the population? Population is the general population. This right here is a sample, not the general. So population is going to be, well, it's going to be women 45 years of age or older. It doesn't matter if they take the drug, because women did not take the drug. They didn't have any effect on there. So it's in general 45 years of age or older. The drug isn't a part of, I don't believe it is. Oh, it doesn't have just 45 years age older. It has ones that do and ones that don't. It should just be all of them that pretty much just live, that are living, at the time. Okay, so what is the sample? So the sample is specifically these 1,013 women who are taking the drug, and some are not taking the drug. So it's not all healthy women 45 years of age or older. That's the population, right? That's in general. So the sample is going to be the women in the study who do not take the drug daily. That sounds right. And then experience a cardiovascular event. Those are the ones who are in the study who do. So that's too specific. We want broader, the women in the study who take the drug daily. So that's the 1,013 women in the study who do or don't take a drug. It's a very odd way of stating the sample and the population, because what they're stating here is what they're doing with the sample and what they're doing with the population. It's just a strange way of saying it. So to try and reason out, population is in general the whole population, the human population on Earth, and then the sample is a much smaller portion, and it's specific to the study. That's the reason why it says in the study. That's the key thing here. The rest of them say all healthy women, and that's too broad, because we only have 1,000 women pretty much. Okay, what is the response variable? Is it qualitative or quantitative? Quantitative. Okay, the response variable are what we are, looking at as a result of the study. In this case, we're looking at if they've experienced a cardiovascular event. Now, cardiovascular event, that's just, kind of like a yes or no question. It's not a numerical, therefore it's not quantitative. Therefore, it's qualitative. It's a yes or no. It's a word rather than a number. If that makes sense. What are the treatments? I believe placebo and the drug, those are what they're actually doing with the people in the study. That's how they're actually, working with them. What type of experimental design is this? It's not matched pairs. Matched pairs would be there's one woman that's doing two separate treatments, I guess, or there's two women that are somehow related. Here we have just 1,013 randomly find women. It's not randomized block design because block design is like, think about like surveying or doing like a census on a population in a community. You look at the different blocks in different parts of a city, for instance. That's randomized block design. You use the people aren't technically independent because they're all living within the same block, but you randomly choose different blocks to test. And of course, here we just have a random group of women. That's why it's completely randomized design. Okay, how does randomization deal with the explanatory variables not control? Okay, so if it's other variables, how does this deal with that? So randomly assigning the women to control groups, the amount of drug each one. No, the amount of drug should be the same in between each woman. Randomly assigning a woman to group for any other explanatory variables, since individual affected by these lurking variables should be equally dispersed. Yeah, that seems right, because if you randomly assign them, then it's reasonable to assume that the same amounts in each population, like different kind of health, for instance, higher blood pressure, whatever might be there, it'll be randomly dispersed and therefore equally dispersed between the two because it's completely random design. Randomly assigning a woman to control group receives a drug and who receives a placebo. No, it's random who receives a drug and who receives a placebo. And then randomly selecting healthy women 45 years of age or older. As individuals in a larger age range might contain lurking variables. No, their larger age range is contained within that. So 45 years of age or older should contain all the ages 45 years or older. So B is the one we want there. Okay, determine the population proportion of cardiovascular events each treatment using a 2-sample z-test. So we're not using the goodness of fit test here. We're using 0.050 of significance. We can do this because we only have two populations, right? Population group 1 and group 2. Sample in group 1 and group 2. So a 2-sample z-test works just fine for this. We would expect it to be normally distributed because it's a binomial, and we should have enough of the. Well, let's actually check. So by check, I mean check the ability to use the 2-sample z-test. There's 3 things we need to check. We need to make sure they're independent, which they are, since it's simple random design. The women were chosen randomly, so we can assume independence. Next, we need n times p times 1 minus p to be greater than or equal to 10 for both of the populations. Now, the p is the proportion of successes. In this case, success is not actually a success. It's a cardiovascular event, so heart attack or stroke. So we have, what was it? Where is it at? 501 in the drug group, 12 experienced heart attack. So 12 out of 501, and then 16 out of 512. So we're going to use that to find P. You have 12 out of 501. Okay, so we're going to multiply this by 501 and multiply that by, of course, it's going to be 12, by 1 minus 0.0239. Just go a few places. And that gives us 11.7. So that's greater than 10. So that one's good. Let's check population 2. We have, well, 16 out of 512 gives us that. And then, of course, we multiply again by 512. And multiply that by 1 minus 0.0312. 15.5. So that one's fine. The last one is that this is no more than 5% of the population. And it's very, very easy to assume that 1,000 healthy women at 45 years of age or older is not more than 5% of all the healthy women 45 years of age or older. So it's safe to assume that. Now we can move on. You always assume that the populations are equal. And I think, let's see. We want to see if they experience a heart attack or stroke. P1 is who take the drug, and P2 is those who do not. So we would assume that P1 is going to be, equal to or possibly greater than. So I think what we want to know is if the drug reduces the amount of heart attack or of a cardiovascular event. But then again, it didn't say anything about it specifically reducing it. Yeah, okay, never mind. I'm just making that up. So it doesn't say anything about the drug reducing it. So you could actually be testing to see if it actually increases it. So really what we're asking here is, are they equal or not? So the null hypothesis should be they're equal. And the alternative says they're not equal. If you see the word like, does the drug reduce or does the drug cause more heart attacks, something like that, that's when you're going to be looking for a one-tailed test, either greater than or less than. But in this case, it didn't actually say that anywhere. I was just making that up. So all we really want to know is, are they different? Oh yeah, it says it right here. Is different. Is it different? So that's what tells you not equal to. Okay, now we can use StatCrunch. And we know this is a 2-sample with the summary. Yeah. Okay, population 1 had 12 out of 501. Population 2 had 16 out of 512. Hypothesis is they are equal and not equal. And the level of significance is 0.05. So that doesn't actually matter for now. We can still do the hypothesis test. All right, test statistic is negative 0.71. Yep, and p-value is 0.479. Okay, p-value is quite large. Make sure of that. Yeah, p-value is quite large, definitely larger than 0.05. So we do not reject H0. There is insufficient evidence to suggest the population proportion and the treatment groups are different. Yeah. Okay, now for the next portion, it's pretty much the exact same thing, except now we're going to be using a chi-squared test. Still the same level of significance, still the same definition, of everything. Once again, we're assuming the proportions are equal. You always assume they're equal or they match the distribution that you want. In this case, that it's a uniform, that both of them are the same. So P1 equals P2, and then of course we're asking if does it not equal the uniform distribution? Are they not equal? Since there's only two of them, that's why it's P1 equal P2, P1 equal. But if there was more, it'd be right. P1 equals P2 equals P3 equals P4, and then P1 does not equal P2, does not equal P3, does not equal P4. That's the idea. Okay, so now we can use goodness of fit. Okay, let's see. I think I don't actually want to use that. I think what I want to do is use a contingency table. Let me figure out what I'm doing here. Okay, so what I've done here is I've pretty much created a contingency table. I have my label group here, group 1, group 2, group 1 being the one that took the drug. Yeah, group 1 took the drug, and then 12 of them experienced a cardiovascular event. That's what CE stands for. And then the other number is those who did not experience a cardiovascular event. All I did here was I just subtracted 12 from the 501 in that first group, and that gave me 489. I did the same thing for group 2, who took the placebo. 16 experienced a cardiovascular event, 496 did not. So if I do stat table contingency with summary, these are the two columns that I'm using, those are the ones that are numbering it, and then my row labels are in column label. And we're doing a chi-square with 0.95 confidence, and that's going to give us this thing. And you can see the table here, it creates the table itself. We get 501 and 512, which you should expect out of the total 1,013 that were tested, 1,013 tested. So all the numbers match up. And now we see we have the chi-square, we have the value, the chi-value, chi-square value I should say, 0.502. And then the p-value of 0.479. 479. Which I believe, yeah, was the same p-value as the last one. And so here again, p-value is way, way higher than the alpha, 0.05. So we do not reject H naught. There is insufficient evidence to suggest the two proportions are different. Okay, now, as you can see, we did the Z value, or sorry, the two sample Z test, and we did the chi-squared test. So two different tests, we got the exact same result. And more importantly, we got the same p-value. So the numbers even come out to be the same. And that's what this last part is talking about. It's asking us to look at the test statistics from the Z, two sample Z test and the chi-squared test and make a conjecture. So the first thing it wants us to do is square the test statistic from part F. This is part G, part F is 0. We clear this off. We have negative 0.71. It's negative, and then we're going to square this. So we're just going to square it. And we get 0.5041, which is pretty much this chi-squared statistic. I'm guessing some of the rounding made it a little bit higher, but they look to be about the same. So the square of the test squared from part F is, let's see, I think they're about the same. 0.5041. 3 places, so 504. And that's correct. So they're about the same. Some of the times you'll actually get the exact same test statistic. In this case, they were nearly the same. I mean, as you can see, the p-values were the same, so that kind of tells you. But what's interesting is that the chi-squared is squared, and the z-naught is not squared. So if you squared that, it's about the same thing as the chi-squared. So maybe the two tests aren't very different.